recording my screen right now, just so you know. If you add something verbally, that's totally fine, but just remember you may be on the recording if you do that. If you post stuff in the chat or you just put up a hand, neither of those things will appear in the recording. I'm just recording the screen. Okay, so I'm going to try and prove that these two sides are equal. Yeah, you all need to go subscribe to my YouTube channel. There's some random stuff on there because I used it for teaching physics, and I've also just put some like other random stuff on there, but nothing I'm not perfectly happy for you to see. So if you want to you know, see what else is on there, go for it. I encourage you to do that. Okay, so so we say, okay, we got to see if these are the same. It says they're equal. Let's try and prove that they're equal. So I'm going to work with the left side and the right side. Let's start by working with the left side. So I'm going to say, okay, left side has got 8 plus 2 squared minus 4 times 5. Well, remember my BEDMAS rules. BEDMAS rules say I'm supposed to do stuff in the brackets first. B is for brackets. So I'll add what's in the brackets first. BEDMAS tells me the next thing I got to do is exponents. Brackets, exponents. So exponents, so 10 squared. 10 squared is going to be 100. Next, I can do my multiplying and dividing. So I'll do that next. 4 times 5 is 20. And finally, my adding and subtracting. 100 minus 20 is 80. So that side is equivalent to 80. Now I'm going to work with my right side. My right side is going to be 4 squared times 5. My BEDMAS rules again tell me I need to do my exponents first. It looks like that one works out to 80 as well. So I'm going to write myself a little therefore statement, but it's going to be a really simple one that I think you're going to like. LS equal RS. Left side equals right side. And we've proven it. We've shown that it's true. They both are equivalent to 80, which means they're equal to one another. So we end this by saying LS equals RS. So we've proven that that's true. That was a pretty simple one, just using basic arithmetic. What if we make this a little more challenging, and now we've got some unknowns in here. We've got some variables. So we're going to try and prove that the left side equals the right side in this case. So let's go for it. I'll start with my left side. I've got x plus 2 squared minus 1. That's my whole left side. Well, x plus 2 squared, what does that really mean? That's x plus 2 times itself. And now I need to get into my multiplying through the brackets. So how do I do that? I do that old, you probably heard of it called FOIL, first outside, inside, last. You may have heard a different name for it, but I got to multiply everything in my first bracket by everything in my second bracket. So x times x is x squared, x times 2 is 2x, 2 times x is 2x, and 2 times 2 is 4. And then I've got my minus 1 as well. Looks like, Kaylee, you're seeing my screen is frozen. Are other people having that issue and seeing the screen is frozen? Just slow. Okay. Thanks, Emma. Kaylee, let me know if that fixes itself for you. Marcia, you're saying yours is okay now. I hope that's the case for everybody. Emmy, you're having some trouble as well. Okay. We're going to try and push through. Thanks for hanging in there. Keep me posted if there are those tech issues. And Jillian, you're saying it's laggy for you as well. Okay. I'm not sure what's going on. We're having trouble this week. Casey, yours is frozen. Okay, I'm gonna try and stop. I'm gonna stop sharing that screen. So I'm just gonna pause my video here. Thanks for letting me know, Kaylee. Okay, so I gotta simplify this expression. So I'll do that by collecting my like terms. So 2x and 2x makes 4x, and I've got positive 4 and negative 1, so that's going to end up being plus 3. So x squared plus 4x plus 3. That's my left side. That's as much as I can do. On my right side, I've got an expression, x plus 1 and x plus 3 in brackets. And I'm going to have to multiply these through, see what I get. So we'll multiply through the brackets. Everything in our first bracket multiplies everything in our second bracket, sometimes called FOIL, or first outside, inside, last. X times x is x squared. X times 3 is 3x. 1 times x is x, and 1 times 3 is 3. If I collect my like terms, I find that I end up with the exact same expression. Cool. So I've proven that that's true, and I'm going to say therefore left side equals right side. And this is a proof that those things are true. This is actually called an identity, what we just did. So I'll explain to you how that works and what that means. We're now looking at trig identities. So an equation, you've seen equations before, a lot in grade 10 and some in grade 9. It's only true for one or two values. Like there's the equation of a line on the left, and there's the equation of a quadratic on the right. Those would have one or two solutions, but it's only true for those one or two solutions. But an identity is a little different. An identity is a mathematical statement that's true for anything, for any value, anything we put in there. So an example would be 2 times x minus 1 is equal to 2x minus 2. And we could see that if we were to multiply through the brackets on the left side, we would get the same thing as the right side. But this is an identity. This is true for any value of x. You could put 1 in for x. You could put 5 in for x. You could put 20 in for x. You could put 1,000,000 in for x. You could put negative 265.3 in for x. It doesn't matter what you put in for x. It's always true. The left side and the right side are always going to be equal to one another. So this we call an identity. And we're going to do some identities today, but we're going to do trigonometric identities, which means sine, cosine, tan type things. We're going to find relationships where things equal one another. And then we can use these to simplify stuff. So this comes up in a lot of complex math that has to do with physics and engineering and design and electronics and like all kinds of stuff. You can use these identities to simplify stuff. So it's a way of making the math simpler for you. So we're going to derive these ourselves. We're going to come up with them kind of from scratch. So to start, we're going to go back to our Cartesian plane, and we're going to label some stuff here. So on my Cartesian plane, I'm going to draw my dotted line up here, and I'm going to say this one is x and this one is y. And we call this one R. We say the point up here is going to be X and Y. So there, I've labeled it. I also want to put on my angle, my principal angle. So I'll write that in here as theta. And so this is how we kind of like describe angles in our Cartesian plane. And now I'm going to write out what sine, cosine, tan are. Those are my primary trig ratios. Sine theta, cos theta, and tan theta. Those are my primary trig ratios. And so I have to remember what they mean. Sine is opposite over hypotenuse. Well, the opposite side of my triangle is y, and the hypotenuse is r. Cosine is adjacent over hypotenuse. So I'll put it as x over R. And tangent is opposite over adjacent. So I've written my sine, cosine, tan ratios relating them to this triangle on my coordinate plane. Of course, I have my reciprocal ratios as well, right? So that's cosecant, secant, and cotangent. And those are just my regular sine, cosine, tan, but flipped over, right? Inverted. So I can actually just take the ones on the left side and I can flip them. This one is going to be r over y. This one is going to be r over x. And this one is going to be x over y. I just took the ratios and I flipped them. So we're going to need to remember these. We're going to need to use these. These are going to help us derive some stuff. So the very first thing I want to show you is this thing called the Pythagorean identity. Now you might have guessed from a name like the Pythagorean identity, we're going to use the Pythagorean theorem. And the Pythagorean theorem, when we're talking about our setup here with our triangle, is the side called x squared plus the side called y squared is going to equal the side called r squared, our hypotenuse. So that's just our Pythagorean theorem. Now what if I go ahead and I divide all of my sides by r? I'm going to take all of those parts of my Pythagorean theorem, but I'm going to divide them all by r squared. So that means I'm going to end up with my regular Pythagorean theorem and I'm going to divide all of the sides by r squared. Well, r squared divided by r squared, that's easy. That's just 1. So that's a nice easy one. Now, x squared over r squared. We got to look back on the previous page. What is x squared over r squared? Oh yeah, here it is. Cosine of theta. Cosine of theta is x squared over r squared. Or x over r. So if x over r is cos theta, that means x squared over r squared is cosine squared theta. So that's just cosine of that angle squared. I can do the same thing for my y squared over r squared. That's just going to be sine. So this is what we call the Pythagorean trig identity. This is an important one. So what I want to do is actually write out all 3 versions of this, and I'm going to ask you to add that to your like cheat sheet thing. This is an important one that we're going to want to use and you're going to want to have at your fingertips. So here we go. I'm going to write all these out. I'm going to start by writing my first one. Let's get a finer pen on that. So this is usually how this thing is written. No, actually, sorry. Let me redo that. We usually write sine first. Not that that's any more correct, but this is usually how it's written. Because I don't know, sine comes first when we say sine, cosine, tan usually. So I'm going to put a red box around that one because that's how it's usually written. No, thank you, not a circle. I would like a rectangle. There we go. Now this one could also be rewritten a couple of different ways, right? I could just use my algebra to rearrange it. I could subtract cosine squared theta from both sides to kind of move it over. So I could end up with 1 minus cosine squared theta equals sine squared theta. This is the exact same identity, but just used algebra to rearrange it. And I could rearrange it a different way, like this. Now, right now, you're probably saying, like, what are we doing with this, Mr. Roy? Well, I'm going to show you in a minute, but what I'd like you to do right now is I'd like you to write these 3 down. So you have them in a nice handy place. So these three things in blue on the bottom, I'd like you to write those on your cheat sheet. As soon as you're done, I'd like you to just type in the chat done, so I know that you've finished that. Okay, so we're recording again. I'm going to go to my next page. Oh, by the way, trig joke. Okay, let's do another one. Oh, thankfully I got an LOL in the chat. It's hard when everybody's mics are off. It's like yelling into the void, but I know you folks like your math humor, so I'm definitely going to keep that one up. Okay, this is our second identity we're going to learn, our second type of identity. This is called our quotient identity. And this is basically the last one we're going to learn, and then we're going to try using it to prove some stuff, prove some things being true. Oh yeah, Marshy, that's right. Everybody chip in $2 and buy me a fake ID shirt. Nice. I used to have so many good math and physics shirts, and I still have a few, but in my university undergraduate physics degree, every year we got some sweet themed physics t-shirts every year. So many good puns. Okay. So we're going to have a look at this now. Let's take sine of an angle and cos of an angle, and let's divide them by one another and see what we get. Well, if we do that, remember, what does sine actually equal in our triangle we drew? Sine is the opposite over hypotenuse side, and cos was the adjacent over hypotenuse side. Now, question is, I'm dividing fractions, right? So when we're dividing fractions, we do that thing called invert and multiply. So we write our first one down like that, and then we multiply it by our second one, but we got to flip our second one. So we change it from dividing to multiplying, and we flip our second fraction, invert and multiply. So that's a little blast from the past, but Dash, you've got a shirt that says "Not flat, we checked" on the NASA logo. That's amazing. Okay, so we say, okay, we're dividing fractions. So when we divide fractions, we can flip the second one and change it to multiplication. That's our shortcut, right? And so we got an r on the top and an r on the bottom. We can cancel those out because that'll just equal 1 when we divide something by itself. And what we're left with is y over x. Now, what does y over x equal? Oh, that's actually our opposite side over our adjacent side. And what's our opposite over adjacent? That's tangent. That's tangent. So it turns out, if you take the sine of some angle, and you get a decimal number, and you divide it by the cos of some angle, another decimal number, if you divide those two, you'll always get the tangent of that angle. So you can actually do that in your calculator. You can go sine of 32 degrees divided by cos of 32 degrees, and the answer you'll get is the tangent of 32 degrees. So sine and cos and tangent are all related to one another. So this is called our quotient identity, that sine divided by cosine actually equals tangent. So I'm going to write that all out, and I'll put a nice little box around it. So tan theta, tangent of some angle, any angle, is equal to the sine of that angle divided by the cosine of that angle. Okay, so that's kind of how that's normally written. Let's put a nice little red box around that. And that one I'm going to ask you to add to your cheat sheet, but I'm going to also put it in two other forms, because I could rearrange this, right? I could rearrange this. I could solve for cos to get cos on the left by itself. So cos of theta is equal to sine of theta divided by tangent of theta. So that's another version of it. I could also solve to get sine by itself, and I would end up with this. Sine of theta is cos of theta times tan of theta. So those are my three versions of my quotient identity. I'd like you to please add those to your cheat sheet, and then I'd like you to tell me that you're done. So now we're going to try using these. Here's all the stuff in one place. So of course our reciprocals we could also call identities. We know they're true for any angle. Cosecant is just sine flipped essentially, 1 over sine. Secant is just 1 over cos. Cotangent is 1 over tangent. So we could also call those identities. And for the 11U class, you've got this in your textbook on page, I think 309. That's all there. But the ones you wrote down on your cheat sheet are the ones that are really the most useful for us. And for the 11M class, you are also going to be doing some of this. Not in quite the same way, but you are going to be doing some of this. And for any of you who go on to take more math, you're going to see this stuff again. Cassie, you were asking about cosecant, secant, and cotangent. Essentially, yes, but what you'll need to know is that if you see cosecant, you can just replace it with 1 over sine. If you see secant, you can just replace it with 1 over cos. If you see cotangent, you can replace it with 1 over tangent. So you will need to know just to be able to sub those in, but that's it. I'm not going to make you do more than that with it for the 11M class. Okay, so we're going to talk about a strategy now for solving, for proving that things are true. So we're going to use these identities to prove math statements. Let's put a little screen on there so I can go one bit at a time. So we're going to prove math statements. We're going to prove that some math things are true. In order to prove it's true, we're going to follow these steps. Number one, we're going to choose either the right side or the left side to start with. Sometimes you need to work with both sides, sometimes you only need to work with one side. So we're going to choose a side to start with. We're going to substitute our identities in. So if I see a tangent theta, I might sub in sine over cos, where tangent was. If I see a 1, I could sub in sine squared plus cosine squared, where that 1 was. So I'm going to sub in my identities. I'm going to use my algebra skills to manipulate it and simplify the expression. And I'm going to show that the left side equals the right side. And then I'll put my little therefore statement at the end. So these are the steps I'm going to follow. And let's go through a question right now where we follow these steps. We're going to try and prove that tangent theta times cos theta equals sine theta. Something that we already know it's true, but we're going to try substituting in to try and prove that this is true. So this will be a nice simple one to start with. So I usually want to start with my more complicated looking side. So I would say that the left side here is more complicated. So I'm going to start with that side here. So on the left side, I'm going to, first of all, write out my left side, tan theta times cos theta. Now I'm going to substitute in my trig identities. I know that tangent theta is equal to sine theta over cos theta. So let's sub that in right now. So sine theta over cosine theta. I'm going to substitute that in. Now I notice I've got a cos on the top and a cos on the bottom. Anything divided by itself just divides out to equal 1. And so all I'm left with is sine theta by itself. And that's actually what the right side equals. So I don't have to do anything with the right side. I'm done. And I can say, therefore, left side equals the right side. I've proven that this is true. Let's try one that's a little more complicated. Here's another one we're going to prove. Ooh, this one looks frightening. We got tan theta over cos theta equals sine theta over 1 minus sine squared theta. Whew. Okay, how are we going to prove that this is true? Well, I'm going to start working with my right side, because to me that looks a little more complicated. And I'll see how I do. So let's start with our right side. We've got sine of theta over 1 minus sine squared theta. And so the first thing I want to do is I want to substitute in my trig identities. I remember that 1 minus sine squared theta is actually equal to cos squared theta. So I can actually just sub in cos squared theta for that. That's one of my trig identities. So where I used to have 1 minus sine squared theta, I subbed in cos squared theta. Now, I think I'll probably stop there because now this looks pretty simple. Maybe I'm going to work with the left side for a little bit. So let's head over to our left side. Let's try and work with that one for a little bit and see if we can get it to equal the same thing. So we've got tan theta over cos theta. Well, tangent is just sine over cos, right? So let's change tangent into sine over cos. Hey Sam, good question. So I'm gonna I'll take care of that right now. I'm gonna put a little circle around it so we know what you're talking about, so everybody can follow along. So Sam, you're asking, why did this change into this? How did I do that? That's actually one of our trig identities. So I'm gonna go back a couple pages here.
Would teachers please dismiss students writing buses north 9 and north 10? Buses north 9 and north 10. Thank you.
And you'll see that's one of our trig identities. So anytime I've got one of my trig identities, I can substitute it in. So good question. Let's head back and let's get rid of those circles. Okay, now I'm kind of dividing fractions here, right? Again, which you remember when we divide fractions, we got to invert and multiply. So I could write this cos theta as cos theta over 1. And then it's like a fraction and I can invert and multiply. So let's do that. I got sine theta over cos theta times, we got to flip my second one, invert and multiply. 1 over cos theta and now let's multiply our two fractions. Sine theta times 1 is just sine theta. And cos theta times cos theta, that is cos squared theta. And we write our squared, rather than above the angle, we write it next to the cosine. And look, our sides are the same. They are equal. So we did it.
Students in first floor odd number classroom. That's first floor odd number classroom.
I wish there was like a confetti effect that I could get to happen here on the smartboard, or like those like party blower, like party blower things every time we get one of these right. So this one I had to work on each side a little bit, and I got them to the point where they are equal. So we proved using our trig identities that these are equal. Let's try another one. Ooh, yikes. Okay, I gotta prove that the following is true. Well, I could work with either side. I think I'm gonna start by working with my left side, and I'll see where I get. So my left side is 1 minus cos squared theta Oh, that's actually one of my trig identities. That's 1 minus cos squared theta is equal to sine squared theta. So I think I've done as much as I can on the left side. Now I need to work on the right side and see if it's going to be equal. I try and prove that it's equal. So here we go. I've got sine theta times cos theta times tan theta. Let's sub in. We always want to start by subbing in our trig identities, so let's sub in for tan theta because that's one of our trig identities. This is why I didn't give you too many of them. So you should be able to recognize if you've got a tan or a 1 minus cos squared theta, something like that, that you've got a trig identity that you're working with. So tan is going to be sine over cosine.
The teachers, please dismiss students in second floor odd number classroom. Please, second floor odd number classroom.
All right, so let's do a little simplifying here. I notice I've got a cosine on the top and a cosine on the bottom. Cosine divided by cosine, that's going to divide out and just equal 1. So what am I left with? I got sine theta, and I've got in here another sine theta. And sine theta times sine theta, well, that's just sine squared. It's times itself. So sine squared theta. We did it! All right. Left side equals right side. So these trig identities tend to be, it's like solving a puzzle, and you got to play with it. Play with the left side a little bit, play with the right side a little bit, sub your trig identities in, move things around, change how it looks with your algebra. One thing I really want to recommend is you want to look at how many terms you've got. So for example, on the left side here we have 2 different terms with a subtraction sign in between them. Here on the right we've just got 1 term. It's 3 things being multiplied, but they're all being multiplied together, which means they're basically one group. So we call that 1 term. So on the right side we have 1 term, on the left side we have 2 terms. We know they're not, if we want to show that they're equal, if we want to prove that they're equal, then we need to change it so that they are either both 2 terms or both 1 term. So sometimes you'll need to add fractions or add pieces together in order to make them all the same number of terms. And making them the same number of terms is something that you really want to pay attention to because it can really help you out. Here's a couple of tips that I think can help you when trying to prove trig identities. So the first tip is convert tangent using the quotient identity. So anywhere you see a tangent, use your quotient identity and switch it around so it's sine over cosine. That's a great place to start. Next one is you want to look for squared terms. So you can use your Pythagorean identity. If you've got a cos squared theta, you can sub in 1 minus sine squared theta. If you've got a sine squared theta, you can sub in 1 minus cos squared theta. If you've got a sine squared theta plus cos squared theta, you can sub in 1. So we're going to look for squared terms and see if we can use those with our Pythagorean identity.
The teachers, please dismiss students in first floor even number classroom. First floor even number classroom.
We're going to compare the number of terms. That means how many pieces are there that are being added or subtracted together? Is there just 1 term? A whole bunch of stuff being multiplied together in 1 term? Or are there several terms? And if there are several terms, we'll need to add them together. And if they're fractions, we'd need to make them a common denominator so we can add them together. Comparing the denominators is the 4th tip, that can often be really helpful in trying to solve these. So you're going to have to play with these a little bit. And if you view them like a puzzle that needs to be solved, and something you just need to kind of play with and try out and manipulate and see how it goes, I think you can actually enjoy it because it'll feel like you're solving puzzles. If you look at it as something where I just follow the same series of steps every time and it always gives you the right answer, you'll get frustrated by these. they're frustrating if you're used to math being just, I follow the same steps, I do it every time, and that gets me the correct answer. Because each of these identities will be solved in a slightly different sort of way. So you really need to view this as puzzle solving and something where I need to play with it for a while to try and get it to work out. Okay? So there is going to be a task that I've posted on our thing. I think I want to change things around though, because on here I said it was due Sunday. We didn't get through quite as much as I'd hoped because of some of our technical hiccups. And I want you to have some time to like ask me questions about this. So I think we're going to have to get rid of that due Sunday. This is a smaller assignment. It won't take you as long as the last one because I know you got test prep coming up.
Teachers, please dismiss students in second floor even number classroom. Second floor even number classroom.